Unit 1 Chemistry, Chapter 3, Metals. So now we're just going to focus on that group. It's the majority of the periodic table, but those group of elements are called metals. We define metals as an element whose atoms readily lose electrons and therefore make a positive ion or a cation. Okay? I remember cation because I think that cats make me happy, so cats are positive. Okay? They form metallic bonds. Yes, I know it's a bit of a tautology saying they're a metal because they make metallic bonds. There you go. And to be very vague, we find them on the left of the periodic table. Okay? They have a distinct set of properties. They have, in general, high melting and boiling points. They conduct heat, electricity very well. They are dense and malleable. And we can explain these properties using a model in which we say the outer shell electrons are delocalized. Okay? So we think of it like this. These are our cations. Okay? These black dots here are representing the outer shell electrons. Now, instead of thinking of the outer shell electrons as going just round and round here, we say that these outer shell electrons can go anywhere they want in this metallic lattice, up and down the layers, in and out of them. And the nucleus and the inner shell electrons stay still, and they make these cations. That makes a really strong multi-directional bond, or non-directional bond, some people think of it as being, because essentially each cation is surrounded by electrons and each electron is surrounded by cations at all times. Okay? So, the more outer shell electrons we've got, the stronger the bonding. So if we go across a period, we get a much stronger bond, and that makes the metals harder to cut. Okay? These cations and electrons can be shared between atoms of the same metal or atoms of different metals. So we can mix them together in whatever proportion we want, and that's what's called an alloy. And we'll look at how alloys are made and how that changes the properties later on in this unit. Okay, so why do they conduct electricity? Well, conducting electricity is the movement of charged particles. Normally, but not always, the movement of electrons. So, if you've just got a lump of metal sitting in front of you, the electrons are moving, but they're moving randomly. But remember that they're all negatively charged. So if we make one end positive and one end negative, by attaching it to a power pack, for instance, then all the electrons are going to go, yeah, and run away from the negative terminus, and they're all going to go, yay, and go towards the positive. And when they all start moving in the same direction, that is electric current. Okay? The non-random flow of charged particles is what an electric current is. And our lattice isn't going to run out of electrons, because electrons will come out of the battery and through the wire and go to those that are lost from around the negative terminus. Cations, they stay where they are. Okay? Now, if we've got lots of electrons that are freely able to move, then we're going to get really good electrical conductivity here. They're also very good at conducting thermally, okay, conducting heat. Because, firstly, they're packed tightly together, so the cations are going to vibrate, and then they're going to bang on the one next to them, and then that's going to bang the one next to it, and that's going to bang the one next to it, and that passing on of vibrations is passing on heat. More importantly, though, and the reason it happens so quickly, is because these free-moving electrons in the bit that you've just heated up, they're going to move really rapidly, and they're going to move into all other parts of the lattice, and as they move more rapidly, they're going to transfer their kinetic energy, which is essentially heat energy, as they go. Okay? More electrons, better conductivity. They're also dense and malleable. Okay? So they're tightly packed because it's a very strong bond. Malleable means that we can move them, we can change their shape, okay? And do that without them breaking. It's basically the opposite of being brittle. Okay? Brittle, you bang it, it shatters. Malleable, you bang it, it changes shape, but it stays in one piece. Okay? It's because we've got this non-directional attraction. So if you bang them, each cation's still surrounded by electrons, and each electron's still surrounded by cations. So they don't really care. They're still both all very happy. They've still got a good charge differential in place. So therefore, we can deform it, and it's not going to break. Now,